lithium-ion batteries. The first speaker today is Mr. Bert Holzpels, who's the founder and CEO of Tanktwo, and he's going to be giving us a presentation on smart cells.
All right, hey everybody. Hope you had a good lunch, so I guess I got an easy time for a while, right? So you guys are just digesting. Let's start off with a question, who knows about us? Seems I need to fire my marketing guy, because this is obviously no good, because we actually make one of the coolest things in the battery industry. So we call it electric fuel to some markets because, you know, it's a little bit controversial, but it gets the attention. So what we actually do is we make cells smart, distributed, and intelligent. And the starting point is, of course, that everybody, at least at this conference, is going to agree with the fact that the world needs better batteries, preferably ones that also cost much less than the ones that we currently have. So the thing that's ongoing right now with the electrification of transport actually helps us out, because even though it is right now perhaps about 50% of all the energy needs related to lithium-ion batteries, it is really a catalyst for change, and that's what we're catalyzing through. So right now, you know, there are a bunch of things that are coming together, which are not necessarily driven by us or by an individual industry. But the thing that is in common with many things is that when they happen at the same time for different reasons, you have this kind of perfect storm situation, scenario, right? So data science, information, management of information, analysis of information, and acting upon it, that is something that increases the efficiency and the utilization rate of assets in many industries. So that's happening now for mobility, specifically through ride-sharing applications. It's happening in the autonomous drive scene. But in the electrification, actually, data science is fairly underutilized. Battery packs are, of course, marvels of technology, the ones that currently go into electric cars and other applications. But data science is something that happens in the lab. It doesn't really happen in the field enough, and that's something that we're trying to change. So one of the direct outcomes of what we're going for here is we're trying to build a business case for electrification of transport where it currently is hard or not yet possible. So the story, everybody's complaining about batteries, they're being too expensive, too slow. I don't need to repeat that here. But why it actually matters for us to look at it slightly differently is that an electric car, like a Tesla, everybody wants a Tesla. I don't think there's anybody here who's going to say that they don't want a Tesla if they don't already have one. But in order to get that down into a price level where it can become a true mass market product, still a step change in development needs to happen. So, but the utility and industrial and professional users of power, they have a totally different mindset about how actually you should approach this. And that is our main actual vertical, how we sell into, even though we talk about electric cars as a skeleton all the time. So the thing about an electric car as driven by a consumer, not by a fleet, not by an Uber driver, is that the utilization ratio is very low. People drive on average in the US 12,000 miles. It's pretty much the same the world over. What good is it then if you have, a battery pack that can take you 200, 300, 400 miles maybe someday? So, because of course you have to invest into it, but you also carry that way around. So, in order to deal with range anxiety, it's just not the best possible solution. So, our solution, Tanktwo solution, is that we make battery packs with thousands of small egg-shaped cells. This is an actual one, I'm holding it here in my hand. 1.5 inches in diameter, shape of an egg essentially. And inside it is, of course, traditional lithium-ion battery chemistry of whatever flavor that the customer prefers. But also a set of sensors, a small processor, and communication capability. On the outside, they have 6 electrically conductive contacts, which all can be wired to the cathode or the anode internally. But because of this specific shape and this specific size, you can put them in a container, in a tank. You can treat them as a liquid, as a bulk solid. So you can have a battery pack, which can hold, for example, 100 kilowatt hours worth of storage, but you fill it up only with 20, because at that day or that moment or for that application, there is no economic need for the remaining 80 kilowatt hours. And then you give your user the flexibility to increase the capacity of the battery pack or decrease it as the future evolves. So There's also the possibility to charge your cells off board. So if you want to have an application with a very high uptime, 24/7 operation, you can do off-board charging and do cell swap. But that's actually a secondary application. So how it works, right, is essentially an intelligence, algorithmic, data-driven approach to putting cells to work. Cells in a specific situation with a certain electrical characteristic should be wired up and could be wired up to serve the needs of the load. Very practical example. Say you would have a battery pack for an electric airplane. So let's say that there's a certain electrical performance required during takeoff, higher drain, and there's a certain electrical performance required during coasting. Maybe the actual, ultimate capacity is maybe the parameter you want to optimize for. So you can throw two types of cells together in a box, and the cells will figure it out how to utilize these cells at what times, in what ratio. So the ability to basically serve your application with the specific performance that the electrochemically active parts can provide and manage that efficiently, that's actually what we do. So the simplest possible business case, right? And this is not necessarily really practical, but people ask that, okay, help me understand what this means. So let's say you want to sell passenger cars to people, but ride sharing is a thing. So you want to have something that where people want to be able to buy a car to commute, where the price point is maybe $20,000, but they also want to have the ability to visit grandma or to do a couple of Uber runs on the weekend. So the solution here is that if you have a battery pack of which you can dynamically increase the capacity if needed and decrease it when it is no longer needed, you do not have this capital investment of capacity and of course the dead weight that you drag around. So since this is a professional audience, I think you're immediately going to see that for an actual passenger vehicle, this is not directly the low-hanging fruit, but imagine if this is a fleet of electric buses for a municipality. You know, a bus that does today a 120-mile route and tomorrow maybe an 180-mile route. There the numbers really add up. And if you ask the CFO, that's an argument that he can work with, right? So more details about that later if you want to dig deeper. So the connected car, that's being talked about by everybody, but quickly planting that into your head here, the connected cell is a thing as well. So a number of reasons for that. You can collect telemetry over the air, you get better information about how they perform under different situations, different environmental constraints, and that allows you to build a better model. Of course, better models on the outset is already a great starting point, but if you see as cells age and as the spread between them grows, having exact information about what is the internal resistance of each individual cell at any point in time, it allows you to have a much better utilization rate, and therefore your cost goes down. So security is a big thing as well, right? So let's say if you have a set of cells that have been used in, for example, a municipal bus environment, and you want to transfer those to another user, so who could, for example, be the local garbage disposal service. So making sure that these cells, which are actually very valuable, so that a cell, and even the biggest optimist in the industry is not going to say that a kilowatt hour of lithium ion chemistry is less than $100. So you want to make sure that everybody is kind of kept under control. So in each of those cells is the equivalent of a SIM card, like you have in your phone. Meaning that if you're the owner and you want that these cells no longer are used, or if you notice that they're used outside of a certain geographically predefined area, or if they're being used in an application which is outside of your terms of service, you can throttle the power or you can shut them down. So lots of things become possible with security and with data. So data science for batteries, really, that's actually what we think is the revolution that is about to happen. So greater utilization, greater flexibility, cells can be pushed very much harder, cells can work longer. A cell can work perfectly down to about 20% of its state of health. And what you can do is essentially, segregate the cells for your application, for your cost structure, for your business model, for your pricing model, for the type of consumer that you're serving. And you're going to walk away with many more hours or many more watt hours of useful life out of a given unit of electrochemically active material. So The point that I'm trying to make here, and also, for example, to my investors, is that data science for asset optimization is really nothing new, you know? You see it in the airlines, you see it in retail, you see it in pretty much everywhere. Most planes fly full because airlines have understood supply and demand, dynamic pricing, channels and so on. Why don't we have that for batteries yet? You need to have the ability to make sure that the batteries are deployed where they're needed most. Same thing, you know, why business travelers are happy to pay much more for a last minute ticket than the average traveler that goes onto, you know, a 6-month planned beach vacation. For batteries, it's the same thing. If you need them right now, for example, think about an ambulance. Waiting is not an option. So for high downtime cost verticals, the ability to be flexible and the ability to price them differently, that is necessary for new business models to arrive. I'm not going to go too much into, you know, the benefits, but flexible pack capacity, you know, changing capacity, selling buses, trucks, cars without the cells as part of the deal, change them at will, reconfigure them at will. You need no more cell balancing. Cells can actually diverge, so you can have a healthy cell and a bad cell, high internal resistance, low internal resistance. You can fix different battery chemistries together. Theoretically, you could even have, you know, nickel metal hydride cells in your pack together with lithium iron phosphate. I'm not suggesting anyone should do it, but logarithmically or algorithmically, that's an easy peasy thing to do. So we're going into that direction that cells are going to have to work harder. So meaning that we don't want to have anymore the situation that cells are actually coming to their end of life where they have lost most of their value from aging. We want them to have most of their depreciation coming from wear. So they should sweat as hard as they can. How we scale, because we're a small company, so initially we sell to a vertically integrated customer, a customer that operates a fleet, operates a service, operates a certain device. The charging infrastructure, the swapping infrastructure, if he so desires, that comes as one package. So we are working on a partnership with a few companies. One of them, for example, is BP. And BP wants to become a power as a services company. So what that means is that we give them, in this context, a number of cells, access to the data, and they decide, you know, which of their customers that they have a pass agreement with actually gets the cells today. Maybe, you know, there are less buses running on the weekend, so therefore maybe more of them could be allocated for private vehicle use. Or, for example, if it's going to be a very hot day, maybe what you can do is that you can use some of those cells in those charging silos, those blue things there. They could be used as grid storage for peak shaving capacity. So if the buses have to do 2 extra swap cycles on that day because power is expensive, perfectly possible. So the transition towards a model where the market for both power and storage is as fluid as possible, that requires intelligence. That's what we do. All right, end of my presentation. I didn't go over time. Achievement for me. Any questions?
Yeah, any questions?
Please, sir.
What about heat dissipation? How do you manage difference
Good question.
in the middle of the pile and outside?
So we used to offer both liquid cooling and air-based cooling. And I'm not sure if it's a good thing or a bad thing, but we haven't sold a single pack with liquid cooling. So the thing is that because these individual cells, they can manage their own state of health, meaning that if you blow air through the pack, so there's 23% empty space between the cells, so you blow air through it. If there's a cell, for example, one in the corner here, well, the pointer doesn't fly, but one in the corner, let's say that it gets less heat extraction because of the way that the air flows, then that cell will throttle itself back. So it goes in what we call a bypass mode. So it connects the 2 contacts that the algorithms have decided to be the plus and the minus terminal. It connects them in bypass. So, for example, it can be on for 75% of the time and off for 25% of the time. So, and then when the thermal stress on the pack changes, that cell is loaded a bit more so that the SOC can be controlled in the way whatever is set by the algorithm. So practical answer to your question is that for applications which are 175 kilowatts peak power load or less, there's no need to even consider liquid cooling, but it is an option. Please, sir.
First, I want to say I really enjoyed this. This is pretty innovative.
Thank you.
The materials level, so it's pretty cool to see some stuff that was solved. How, if you could estimate, how much loss do you assume is due to resistance between the individual cells?
So the question was about how much electrical or thermal loss there would be because of contact resistance between the cells. So the type of customers we sell into, we actually give them the option. So we have essentially two contact alloys. One is a combination of nickel, tin, and a third metal plated over copper. So the contact resistance is in the order of magnitude of a few milliohms. So, but since we inside of a pack, see actually if I can pull up that slide easily. So inside of a pack, we have a very large amount of parallel strings. So the actual current through the cells on average is less than an amp. So the influence of the contact resistance is almost negligible. So, but to finalize my argument, so you can actually decrease still the contact resistance for applications where this matters, for example for defense, where cost is less of an issue and ultimate performance is. So there we offer the option to actually do gold plating. And then finally, and this is not shown in these diagrams, but each of these packs, they have an actual mechanical actuation mechanism. So a few options. The most popular one is an inflatable silicone bladder inside the tank. So when the filling is done, that bladder is inflated and it applies pressure on the cells. So and it turns out that contact resistance is not an issue. Thanks for your question. Yes, sir.
Yeah, so your cells have a brain, and I'm wondering what is part by weight or by volume of this brain, right?
Good question. So the question was that how much do we lose because of the brain? So you guys know here that batteries don't follow Moore's law, right? So everybody expects that in a few years you're going to buy a 100 kilowatt hour battery for $250 from Costco. Well, that's not going to happen because physics. So, however, we do benefit from Moore's law in terms of silicon. So the intelligence of this thing, and it's not entirely correct, so it's just an illustration, but the intelligence of these cells is not much higher than what you find in a musical greeting card. So it's a simple, low-power processor that does perfectly fine what it has to do, but it doesn't have to be very smart. So actually all of the things that really matter, such as the cryptographic stuff, so that is in custom hardware, and it takes almost no silicon at all. So the direct answer to your question is how much do we lose? We actually do not lose anything at all, because inside, actually you can see this on that picture over there. So in the spindle, there's a small circuit board with a chip on it, and that actually would be more or less lost space anyhow. So if you use a different winding technique. There are a few other options. So if you compare an 18650 or cylindrical cell-based pack with ours, it's pretty much a wash. Thanks for your question. Yes, sir, in the back.